Air flows at 5 meters per second on top of a 20 centimeter square plate. That 20 by 20 is usually not there. I've put it to help you guys out because that's a very weird sentence. Like, it can get some students confused. Like 20 centimeters square plate means it's 20 by 20, okay? That's confusing, so that's why I put it there. Located in a ventilation duct. Far from the plate, the ambient temperature is 10 Celsius, and the average temperature between the hotter plate and the flowing air is 90 Celsius. The plate is not at a constant temperature, okay, so non-isothermal. However, transfer heat at a constant flux into the flowing air. So there's a constant heat. So we have a constant heat in a non-isothermal situation. A, what is the heat transfer from the surface and what? So we want to know what is that constant heat that is transferring from the surface. What is that heat flux? And B, determine the heat transfer coefficient H at a distance of 3 centimeters from the edge. So it wants to know what's H at X equals 3 centimeters. Okay, so let's start with my beautiful drawing of a plate. And I'll make some questions. I'll give you guys some questions for us to be able to fill in the blanks here. So this is 20 by 20. Guys, tell me, what is the temperature of the plate? What is the temperature of the plate?
At least 100 degrees.
At least 100 degrees. I like that answer. Why is it at least?
The temperature changes across the plate.
Okay, right on. And why'd you come up with 100? It's all correct. Just want you to explain for everybody else.
I came up with 100 because the temperature difference is always 90 degrees. So at the very beginning of the plate, T infinity is 10 degrees, and there's a difference of 90 degrees, which means the plate is 100 at least.
Brilliant. Okay, so check it out. It's very tempting for a student to do this, right? Because you see the 90 there, you're used to putting the things there. But what the thing is saying is that the difference between the two, the average difference, I'll put that bar there, is 90 degrees Celsius. Okay, and because we know T infinity is 10, then the average, because the average is 90 and 10, so that will be at least 100. So that's why he said it's at least 100. Okay, so 100 down here. Okay, watch out for that. So the plate is not at a constant temperature, but the heat flux is constant. So I'll give you guys, again, let's see, I'll pause the video. So we have a couple of options, right? If you guys go down to the third page of the PDF I send you, we could use the first two equations of the third page or the last equation of the second page, right? So it depends on our Reynolds, right? If you notice, the difference between them is the Reynolds. So whether it's turbulent or laminar. So let's go ahead and find out what is this system here. If Reynolds for this whole system is turbulent or laminar, and then once we do that, we can eliminate and choose only one of those equations there. Now, to be able to find Reynolds, I first need my properties. So let's start with the properties. I'm doing properties at 55, right? So check it out. My T film will be 10 plus 100 over 2, which is 55 Celsius, which is the same thing as 328 Kelvin. So this is air, so I'm going straight into table A5, and I'm extracting everything I need there. So density, this is at 1 atmosphere, so I'm safe. I'm getting density, viscosity, Prandtl, and conductivity. Okay, with these guys here, I'll find Reynolds. So my Reynolds will be my density. It'll be my velocity of 5. The length of this guy is 20 centimeters, so 0.2 meters, and this is 1.96 10 to the minus 5. So I got 5.5 times 10 to the 4th. Turbulent or laminar? Okay, so that means there are two equations that I can use for this to solve this problem. And I'll use both of them. It really depends on what you want to find, because they're both applicable. It's just a matter of what you're trying to find. This one here, let me open it up. L over Q 0.6795. Reynolds half. Reynolds third. This is one of them, right? And the other one is Nusselt at x equals 0.453. Reynolds at x to the 1/2. Reynolds to the 1/3. Okay, so those are the two equations we can use because this is a laminar system. Now, what's the first thing we're being asked to do? First thing, part A is asking us, what is the heat transfer from the surface in watts per meter squared? So in other words, what is our Q flux, right? The flux of energy. So it's asking us, what is this guy here? So obviously, if I want to find that guy there, I'm going to use the first equation. The second part is asking us, what is the convective coefficient at 3 centimeters? So to do that, I'm going to need Nusselt, so I'll use the second one. So let's start. A. I'll copy paste this one here. Okay, so what is the difference, the average between my wall and my infinity? I know that already because it was given as 90, right? Celsius or Kelvin, doesn't matter because it's a difference in temperature. Okay, Q is what I'm trying to find out. What is the length? That's 0.2. What is my K? 0.028. Reynolds I just found to be constant, doesn't change. Just found Reynolds to be 5.5 times 10 to the 4th. What are my 5s? That's to the 1/2, and my Prandtl is 0.7025. Okay, so if I'm solving for my little q, lowercase q, I get 1,784 watts per meter squared. I'll leave it to you guys to check the units on this. Afterwards. So that will be our first answer for A. Okay, and then B is, what is the convective coefficient at 3 centimeters? So this guy has 20 centimeters length, and he wants to know at 3 centimeters. Well, obviously it's going to be laminar flow because the whole thing's laminar flow. So 3 centimeters is obviously laminar flow. So we can go ahead and do part B. We can find our Nusselt at x equals 3 centimeters. And to do that, we can apply this equation here. The only thing we need to keep in mind is that, just remove this guy. The only thing we need to keep in mind is that this guy, so x equals 3, is that this, where is it? this Reynolds here is also for the local one, right? So if I go ahead and now and plug Reynolds as 5.5 times 10 to the fourth, that will be incorrect, because that's the Reynolds of the whole length of the plate, right? At x equals L. And at the moment, I want Nusselt at 3 centimeters, so I'm going to have to find Reynolds at 3 centimeters. So let's start by finding Reynolds at 3 centimeters. So Reynolds, everything else is the same, 1.08. Velocity is still 5, but now it's 0.03 meters, right? Not 0.2 like it was before. And my viscosity is still the same, 1.96 times 10 minus 5. So my Reynolds is, my Reynolds? 8,260. Still laminar, obviously. So now I go over here and I do. And I got this to be 36.61. If my Nusselt is 36.61, then my H is trivial, right? My H becomes trivial. Let's do it in big bold letters now. Because we know Nusselt simply H, L, or X for this matter, over K, therefore H at X equals 3 will be just Nusselt 36.61 times K, which is 0.0286, is it? No, 28, divided by 0.03, which gives me 34.17. Now, as we are going down this plate, we would expect our H to decrease all the way until we reach the critical length. Then turbulent flow kicks in, and turbulent flow helps the thermal transfer. And then we observe the same behavior. It starts to decrease again. Okay, so we'll go into the, you can actually see the graph. We'll go into the graph on question 2, but you can see the graph on the second page, the second page, the first slide. You can see the behavior of how the convective coefficient changes as X increases. Question